Hello. All the questions that are covered here were were given to me by my attempt at Pop Quiz 10. I think it does a good job of spanning all of the content that you are going to be responsible for on exam 3B for Friday. So this question is about roles in the equilibrium. All right, so let's make a summary. First of all, acids are either neutral carboxylic acids or any carbon, oxygen, hydrogen, the hydrogen on a carbon, oxygen, hydrogen, or any positively charged species. Water, when in the equilibrium of these acids, will start as a reactant H2O, convert to H3O+, and will undergo Ka. Bases will be the negatively charged oxygen or the neutral nitrogen. In this case, water will, as a reactant, will convert to hydroxide ion, which is a base, and this will be Kb. When we look at the reaction given to us, we see hydroxide ion as a product, and so we know we're working under Kb. Now we don't know, we have a carbon and hydrogen and nitrogen and oxygen, so it's a little bit hard to know from the structure of whether it would undergo Ka or Kb. Just look at the formula of A. But since we're given the product of hydroxide ion, we know it must be Kb. All right, in Kb, water acts as an acid. It forms its conjugate base, hydroxide ion. Under Ka, water acts as a base and forms its acid conjugate. So that's really important to make sure that you have summarized these types of interactions. So once we identify water's role as an acid, that means A must be a base. And if that's a base, then its conjugate acid must be there. We also know that it's an acid because it has a positive charge. So that was another indication that we would know for the identity of all of the bases. So the bases have to be A and they have to be D. Okay, so this is a question in which we're asked so here's an acid. We know it's an acid because we're shown a carboxylic group. And we're told that we want to pick one of these, out of these four compounds below, which one would be weaker due to inductive effects. Well, when we look at the acid group, what we see are a stabilizing effect and a destabilizing effect of the conjugate base. The stabilizing effect is the oxygen that is between the two carbon atoms, and the destabilizing effect are the carbon atoms that are shown up above. So what we're going to do is start analyzing it. So the acid strength in feature 1 is O versus S here, and what we see is, right, S minus would be more acidic. It's a more stable base than O minus. And feature 2, we're just going to go through the different features here. Feature 2, are there any differences? And the answer is no. There's no difference because all of the groups are shown with single bond, double bond resonance. And so this additional stability by resonance, all groups, all of the options, A, B, C, D, all have it. Feature 3, which is inductive, right? Now we have to analyze how the group is stabilized by induction. So the carbons destabilize the base, so that would be less acidic. The oxygen that's present in the group stabilizes the conjugate base, making it more acidic. All right, so that gives us some insight into how we're going to pick the answer. So chlorine stabilizes the base because this would be answer A. And answer A, chlorine is stabilizing the base, making it more acidic. So A is more acidic for inductive effects. D is more acidic for inductive effects because both of these A and D are removing carbon atoms that are destabilizing that lower acidity and replacing them with stabilizing electronegative elements. So there are three more acidic acids here. The SH is more acidic for feature 1. Sulfur is more acidic in the same group than oxygen. Then we have A and D, which are more acidic, but they're more acidic for inductive reasons because they are stabilizing the conjugate base through induction. And the only answer that is decreasing acidity using inductive effects is answer C, where we have the removal, right? It's missing the oxygen, and that's creating a weaker interaction. It's replacing an oxygen with a carbon atom, and that ultimately would lead to a less acidic molecule. So that's how you use these features to analyze aspects of the molecule to determine acid or base behavior. Okay, so here we're asked to rank the acidity of acetaminophen, naproxen, and aspirin. Right, so the first thing we're going to do is take a look at the conjugate bases that would be formed from each of these groups. So acetaminophen has resonance. It has a single bond, double bond, but it's attached to carbons. Then we have a carboxylic group with carbon atoms attached, which is naproxen. Then we have aspirin, which is also a carboxylic acid, also has carbons attached, but has increased resonance. So now we're looking at, well, how are we going to rank this kind of acidity? Then the first thing we would see is that the most acidic would be aspirin because it has extra resonance, it has a carboxylic group. We expect more delocalization, which is going to lower energy, increase the entropy of the solvent, leading to more acidic behavior. So aspirin's the most. That was answer B or D. And then when we look at the difference between acetaminophen, which is just an alcohol, a C-OH, yes, it does have resonance, but it is not delocalized across the carboxylic group. And but naproxen is. So we would pick naproxen as the next most acidic, and the least most acidic would be acetaminophen. That would give us answer D. So remember, we're looking at the most stable base that can be made. The most stable base would be the most acidic. The least acidic is going to be the least stable, the least delocalized. It's much more effectively delocalized across multiple oxygen atoms, oxygen, carbon, oxygen, than it is through carbon atoms. Right, in this problem, we're asked for phenoprofen. Is it Ka or Kb? And what is the reaction? Right, so the first thing we do is we look at its functionality. We see a carboxylic group, so we know it's going to undergo Ka. All molecules that have either a neutral carboxylic group or a positively charged amine will undergo Ka. And that, when you react with, remember, water is acting as a base, so it's accepting the proton from the acid under Ka. So we'll write the reaction this way. C15H14O3 plus water. We have to create a negatively charged ion. It lost a hydrogen, so now we only have 13 hydrogens, O3 plus hydronium. So it's a Ka reaction. We needed to produce hydronium, and we needed to lose one hydrogen as it was transferred to water. So this is a problem in which we're given a pKa, and we're told we're placing this molecule at a fixed pH equals 4, so we're putting it in a buffer of 4. I know it doesn't say buffer, but because we're given a fixed pH, we're assuming that it is a buffer. We want to know which of these pairs is most abundant in the solution of C. All right, so the first thing we do is we need to recognize that pH equals pKa is a very important value. And the answer, and you say, why is that? And that's because any pH below pKa, the acid form is most abundant. Any pH above pKa, the base form is most abundant. And so that's really helpful because we're given pH here is 4, and the pKa is 4.8. Now, when we look at the solvent, water, right, basicity and acidic behavior, there we use pH equals 7. So any pH below 7, H3O plus is most abundant. Any pH greater than 7, it's hydroxide ion. All right, so now we're given, we can make a table here. Any pH less than 4.8 has the acid form as most abundant, C8H16O2, it's got to be neutral, and hydronium. Any pH between 4.8 and 7, C3H15O2 minus the conjugate base, because we're above the pKa, is most abundant. But since we're still acidic, the pH is below 7, hydronium is most abundant in the solvent. Then above pH equals 7, then we still have the same conjugate base of the weak acid as most abundant, but now we're turned into a basic solution, and hydroxide ion is now most abundant in the solvent. All right, so one is the weak acid, weak base analysis, which is done just by pH versus pKa. And then we have the solvent analysis, which is done comparing pH to 7. So we're at 4, we're here, and that gives us answer B, right? We have the neutral carboxylic group in most abundant since pH is less than pKa, and we're acidic, pH equals 4. Which of the conjugate pairs could be used to create a buffer solution? All right, so let's make a summary of what we know about buffers. First, they need to be weak acid, weak base pairs. In this selection, hydroxide ion is not a weak base or weak acid. Nitric acid is not a weak acid or weak base. These are strong substances that you need to recognize by formula. So strong acid, well, that's really acid. Strong acid, HNO3. So what else do we know about buffers? Well, one is that we have the Henderson-Hasselbalch equation. Right? This can be rearranged to solve for pKa, which most questions ask about. And so we use this when we know the ratio, we know the concentrations of A minus and HA, we're given pKa, and we're asked for pH. The other type of question that we are asked is, what is the concentration of HA or A minus, or the ratio of the concentrations? In that way, we could use this formula, pH minus pKa, raised to the 10 power gives us this ratio. We can also solve for the acid over the base, and in that case, it's pKa minus pH. So given pH or pKa, we can find the ratio. Sometimes we're given HA, and we're asked to find A minus. So those are all the different possible questions we could ask you for buffers. We could also see it on this side. We're given pH and pKa. Sometimes we're given the concentration of A minus. And then if that's given, we can calculate the concentration of HA by solving for it, which we're going to do in the next problem. This kind of gives you an idea of everything that we're focusing on in terms of buffer. 1, what can be a buffer? 2, how do you calculate the pH knowing pKa and the ratio? Or how do you find the ratio given pH and pKa? All right, so here we have a question in which We're given a Ka, which we can convert to pKa. That's usually what we have to do for all acids, all buffers. And we're given a pH, and we're given a concentration of the acid. And asked what is the concentration of the conjugate base to make the pH equal 5. All right, so let's take a look at how we would set this up. So since we're dealing with the ratio, we would be using the 10 to the pH minus pKa version. Now in this case, well, we need pKa, so let's take the minus log of the Ka given, and we see it's 3.7. So what we're going to do, 3.74, so we put 3.74 in, and we see that the ratio of A minus to HA has to be 17.8. Right, now we're given the concentration of HA, so we can solve for the concentration of A minus, HA times 17.8, and we do that, we get 2.1 molar. Right, so that's how we would do a problem in which we're given the pH and pKa and asked for one of the two concentrations, given the other. An equal number of moles of benzoic and its conjugate base, sodium benzoate, are added to water. Which statement correctly describes the solution? All right, so what we really want to know, so with this information, we can find pH, because that's what we need to know to answer this question. If you have equal amounts of the acid and base, then that is the definition of the optimum buffer zone. And that's where pH equals pKa, because now you have the ratio of 1, because they're equal concentrations, and pH equals pKa. So the pKa of benzoic acid is 4.2, which means the pH is 4.2. So there's an acidic solution. POH is 14 minus 4.2. If we look at that, that's 9.8. So we have much more hydronium ion than we have hydroxide ion, because it's an acidic solution if pH equals 4. All right, so when we look at the options here, the correct option we would pick here is that the pH is less than the POH, meaning an acidic solution. An unknown acid with a concentration of 0.015 molar has a pH equal to 2.5. Determine pKa. Right, so now we're going to sort of summarize all the equations from Unit 6, Module 2. We obtain this equation by using ice tables. Now, hydronium is rarely given. We usually have the pH, so we can sort of put this in the form of pH. That would be 10 to the minus 2 times pH. It's 2 because of the square. Square, when you're doing logarithms and powers, we can include it this way, all over C0. We also can solve for C0. C0 here is going to be almost the same thing, 10 to the minus 2 pH, but divided by Ka, or 10 to the minus pKa. So these are really useful equations to have because we're often given pH, we're often given pKa. But in this problem, we want to solve for, and then the third equation is to rearrange this for hydronium ion, and we get the C0, square root of C0 times Ka, which we can rearrange to 10. So these are equations you want to make sure you have available for weak acids. All right, so we're going to be doing the top equation because we're asked for Ka. So let's do that. We know pH is 2.5, so we just plug it in there. 10 to the minus 2 times 2.5 divided by 0.015. And we do that, we get 6.7 times 10 to the minus 4. So that's the value of Ka, but we're asked for pKa. So we're going to need to take the minus log of this value. So the minus log of 6.7 times 10 to the minus 4 is 3.2. So the pKa of this acid is 3.2, and this is how many many Kas of acids have been determined. You make up a known concentration, measure the pH, you can calculate pKa this way. Let's see, we did that one. Next one, vinegars is used for cooking. And now what we're saying is we're given, determine the pH of a solution that's 0.87 molar if we're given pKa. Right, so now we can use the third equation we just introduced, which is C0, square root of C0 times 10 to the minus pKa gives us hydronium concentration. So when we plug this into the formula, we get that the hydronium ion concentration is 4 times 10 to the minus 3 molar. So the square root of 0.87 times 10 to the minus 4.74 gives us 4 times 10 to the 3 molar. The minus log of 4 times 10 to the minus 3, which gives you the pH, is 2.4. So we expect this solution to be 2.4. Acidic. Right, so lots of students ask questions about this in office hours, so let's kind of go through the analysis and trends of pKa and pKb. So we can determine pKb for each of these acids. It's really convenient if you do that. And what we see is Tylenol is the weakest acid, but the strongest base. Aspirin is the strongest acid, but the weakest base. And ibuprofens are in between. So let's take a look at a couple relationships that are important. pKa plus pKb equals 14. As pKa goes down, the acid is stronger. Ka is 10 to the minus pKa. pKb, when pKb goes up, the weaker the conjugate base. And so when we look at these problems, now we can sort of use this as the way we can analyze it. So let's say the conjugate base of aspirin is stronger. No, that's wrong, primarily because aspirin has the weakest base because it's the strongest acid. Its pKb is much bigger for aspirin, right? Aspirin's pKb is highest. The conjugate base of Tylenol, now that's the strongest, is stronger than ibuprofen. Absolutely. It's the weakest acid, but it's got the strongest conjugate base. Tylenol is a weaker acid than aspirin. Absolutely. Aspirin's the strongest. It has the lowest pKa. Ibuprofen is stronger than aspirin. That's wrong. So 2 answers correct here. Really important to make sure, and it's easy to get mixed up, so I really encourage you to write out all the pKa's and pKb's of the comparisons you're making. Right, so here we're asked to calculate the pH of 0.1 molar of this substance. All right, so now we're going to be working with the base equations. So first thing we see is using the Henderson-Hasselbalch equation. If we know we have the same amount of A minus over HA, which is at the 50-50 mark, we know that pH equals pKa. So we see the pH here equals pKa, and we can obtain the pKa as value is 10.2. Now the problem begins, because what we know is any neutral nitrogen molecule undergoes pKb in water. So pKb in water, neutral nitrogen, and so and all neutral nitrogens undergo pKb in this way, take on positive charge with hydroxide ion. Right, now let's look at the equations of that. So that means it's very similar to the acid equations, except instead of hydronium, hydroxide ion is present, and instead of Ka, it's Kb. All right, so the first thing is hydroxide ion is equal to the square root of C0 times Kb. All right, so, or 10 to the minus pKb. So we have C0, it's 0.1 molar. We have pKb now, 3.8. So we can use that equation. But just for the sake of completion, these are the other 2 equations, hydroxide ion squared over C0 or hydroxide ion squared over Kb. You can also put in the form of 10 to the minus POH. And those are also pretty valuable equations, depending if you're asked to calculate Kb or calculate unnecessary concentration. But here we're asking for pH, which is often the case. And so, so that means that we can calculate the value. So let's do that. So hydroxide ion is, so hydroxide ion here is equal to the square root of 0.1 times 10 to the minus 3.8, which equals 4 times 10 to the minus 3. So minus log of 4 times 10 to the minus 3 molar. It's 2.4. That equals POH. So pH is equal to 14 minus POH. 14 minus 2.4. 11.6, which is basic, which is what we would expect. The answer is B. Right, so here we have a question where we have a molecule, and the molecule is, and we're adding more, it's in equilibrium, and then we are adding more reactant. Now we're asked which Q versus T graph best describes that. Right, so first we recognize that we're under Ka. We see the COOH group, and that's going to create its conjugate base plus hydronium. Okay, so that's our equilibrium. And that's important because we're going to need to write the equilibrium expression, which is, I'm just going to abbreviate as DOB minus. Okay, so let's see a little problem here. DOB and since we are working under Ka, it would look like that. Oh, looks like I did it twice. Right, so that's our value of Q, and it's equal to all of these equilibrium concentrations. Right, that's K. So Q equals K, and now we're doing a stress, right? We're changing the system by adding a reactant, and if we add a reactant, then Q has to go down, right? Q goes down because the reactants are in the denominator, so this went up relative to K. So that would give us the top two as possible options. And because Q went down, there has to be a shift to products. You have to make more products to increase Q. And that's what we see in both here, that we have to shift to make more products. And then we reestablish equilibrium. And so now the question is, what happens to the pH here? We got that's the difference between these two options. And now we just look at the role of the reactant. The role of the reactant is an acid. We added more acid. pH must go down. That gives us this answer. All right, so we also have questions like this in which you don't have a Q versus time graph. What you have are just in words. What happens? Does Q go up? Does Q goes down? And what happens to the shift? Right, so let's do that. Here we have another problem in which we are given the equilibrium, and remember Q is, in this case, we're just going to look at products over reactants. That's what Q is. it's proportional, Q is proportional to products over reactants. And so if we add reactants, Q goes down versus K. And that's true with all these options. But the shift, right, the shift has to go up. The corresponding shift has to go up to reestablish the Q equals K. And that's what separates some of our answers here, because the first two, right, say decrease, that Q has to the shift must decrease Q, and that's not true. We have to increase Q. So that means that the last two options are correct. And now one of them is correct, and say what happens. Well, how are they different? Well, they both say that the shift Q must increase. We agree with that because it initially decreased, so it's got to respond in the opposite way. And now what do we know about what happens to the products? So if we add reactants and we shift to products, then the product concentration should increase. We should have more products. And that tells us the difference here. D is definitely incorrect because it says the product concentrations, which are fluor F minus and H3O plus, go down. So we know that they have to go up under the shift to products, and that gives us answer C. So the more practice you have with shifting and using these kinds of arguments, the more reliable they will be. We could also look at this problem from the standpoint of the kinetic argument, even though it didn't ask for that, but we haven't seen the kinetic argument yet here. So let's do that. So step one is that the rate forward is equal to K forward times HF, and that equals rate reverse K reverse F minus HF. H3O plus, right? So that's our kinetic argument, right? If we wanted to make the kinetic argument, just for practice. All right, so that's it. And now what are we doing? We're adding reactant, so that means the rate forward has just gone up, because HF just went up, and it's running much faster than rate reverse. Because K, nothing's changed here. We didn't add products, we just added reactants. Right, so rate forward's going up. Because it's going up, there has to be a shift to decrease rate forward. And the way we decrease rate forward is shift to products. So we have to have less reactants and more products, so we shift material over, and then concentration, so that means F minus has to go up, H3O plus has to go up, pH has to go down. And step 4, now the rates are back the same. So I know the initial problem was the thermodynamic argument, but you also want to make sure that you're prepared to do the kinetic argument. Right, so what we're going to do is add water. So if water is added to the system, this is a much more complicated problem than just adding reactants. So let's kind of go through this in detail. Now, water is a reactant, but is not allowed to be in Q or K or rate laws, not directly. So the way water is affecting all of the substances here by the addition of water is not through any act on on Q or rate laws directly, but just to lower, if you add water, you just lower all the concentrations. And that's the key to water problems, is you don't think of water as being in the rate law directly or being in Q directly, but it just indirectly changes all the concentrations. If that's the case, Q, we write Q, all concentrations. So initially, we're at equilibrium, right? That's our initial equilibrium. And now, if all concentrations go down, Q goes down more on the top than the bottom because there's two concentrations available. So overall, Q goes down, more than K. Right, so Q goes down more than K. And so one of the things you can think about with water is that whatever happens to the concentration happens to Q. So if concentrations go down, Q goes down. Concentrations go up, Q goes up. So we know Q goes down, and that makes the top two answers again very consistent. The shift has to go up. You have to shift up to go back to Q equals K. So to find pH, we just look at the role of water. When we are adding water, in Ka, water functions as a base. And since it functions as a base, it will increase the pH since you're adding a base. So just kind of keep that in mind. Q is directly proportional to concentration. Add water. If you add water, Q goes down because concentrations go down. Remove water, Q goes up because concentrations go up. All right, so those are all of the ideas that are in Pop Quiz 10. I sort of elaborated on them. So I'm just going to make a quick summary here of Module 1. These are the ideas you want to make sure that you have in mind. Acid-base reactions undergo Ka and Kb. They are always reactant favored. Reactions with water, if they're acids, undergo Ka where they make a base plus hydronium. If it's Kb, a base in water will make its acid form plus hydroxide ion. HA is any neutral COOH group, or N+. A minus here is any negatively charged carboxylate group or a neutral nitrogen. These are the acids and bases that undergo these equilibria. When you place these groups in water, they change the pH, which is the minus. Remember, pH here is the minus log of hydronium. So acids will increase the amount of H3O+, but it also makes pH go down. Bases increase pH. So OH minus goes up, H3O+ goes down, and in that case, and that's what bases do in water. In this particular equilibrium of acids, water acts as a base, and when the equilibrium has A minus as a reactant, it acts as an acid. Water acts as an acid. All right, in Module 2, just a general summary in terms of the calculations. So, as we said in the other problems, remember there's 3 different calculations that you have to be careful about. One is if you're given hydronium or pH and C0, you can calculate Ka. And you can rearrange that equation for the other 2 variables, either C0 or H3O+. It's always nice to have these equations in forms that you're often given the values. So given pH, given pKa, they're very convenient. If we look at bases, again, very similar, except we're dealing with Kb and hydroxide ion. So then we're dealing with POH. Whoops, sorry. Okay, I'll just leave it like this. So you can, you're dealing with POH instead of pH, Kb instead of Ka. And we do that, we get the exact same value, but what you have to be careful about, like exact same equations for the most part, look the same, but in Kb, what you have to be careful about is you're calculating hydroxide ion first, then you have to calculate POH, and then you calculate pH. So that's the story about base calculations. And then finally, shifting. We didn't get to do the kinetic argument. We only did the kinetic argument once, but in general, we construct kinetic arguments by first you have an equilibrium, and then you disturb the equilibrium by adding something. So the rate forward, so the way we construct the argument is rate forward is Kf times the reactants equals K reverse times the products, K reverse times the products. That's our first step, or this is the definition of equilibrium. Equal rates, forward and backwards. Right, so if we add reactant, what we saw is K forward goes up. It's moving faster. Shift to products. If you add water, all concentrations go down, but the reverse reaction is always much more affected by water than the forward because there are two concentrations present. Since K reverse is moving slower, since the backward is moving slower, right? Slower. We are also going to shift to products again, but all concentrations go down. And then if we add a strong acid, which is adding a product to Ka, the reverse reaction is now moving faster because H3O plus just went up, and we would shift to reactants. So that's how we build these arguments for kinetic arguments. And like I said, we explained this in the video earlier. I did that for thermodynamic arguments, but we didn't have the same equivalent summary for kinetics. Okay, so with that summary, I would say that is all of the content you will need for the test. I really encourage you to practice each type of question and be prepared for it, since it's very likely you'll see them on a test. Good luck.